Right? So we're gonna first learn the basics of maximum and minimum value problems, and then we're gonna put that into a more conceptual idea. Okay, so and maximum and minimum values we're about to learn here is an application. So I've been mentioning it earlier. At this point of the quarter right here, it's all about we're learning different applications of why it's important to find the derivatives and all that, and then tangent line and all of that. So now specifically about maximum and minimum values problem. So let me quickly bring up a sketch of a function, some kind of function, any kind of function. So x-axis, y-axis. And so we've been knowing it, the output function. So we got a function f of x, y equals f of x. So the x is the independent variable, and we call it, it's the input of the function, and then the y here is the dependent variable. We've been calling that the output of the function. And so any function, when you put in a graph, then graphically you can have something like this, going up, going down, and going up and going down. Okay, and so, and now when I'm talking about going up, going down, I mean like as we change the x input values, as we change the input values for the x values, and that means as we going from the left to the right on the graph, then you can see, we can observe that the function value with the vertical values, because vertical values on the graph is representing, from what we've learned from pre-calculus, the vertical value is the output of our function. And so as we keep going up, as we going from the left to the right, for a graph I drawn like this, then the function value is going up, going up, going up, going up, and it hits a certain height right here. It hits a certain vertical values, and then it start dropping. Okay, it start dropping, and then it drops to a certain low right here. Then it stops dropping, and then it keep rising back up again. So we have all of that nature about up and down and up and down all over. And so in that way, we come up with a certain observation. So in the way how I'm seeing it, we will get more precise into the detecting those. But in the picture that I'm drawing right now, okay, we do notice there's a certain point, say, let's call it x equals a right here. At that certain point, the function stops rising, okay, and then it's going to start falling. So falling, once again, the y value will get lower and lower as we go further to the right hand side. So x equals a is a point where the function stops rising, because it was rising. As we getting x going from the left to the right, the function value was rising, but rising up to that height right there, and then it's going to stop rising, and then it starts falling again. And then on the function, again, we will learn how to detect this more specifically. But we have, let's say, another value. Let's call it ax equals b, for example. At this point right here, what's special on the graph right here is that the function stops falling. So the function was falling before that. So anywhere before we came to x equals b, then the function was falling and falling and falling, and then it stops falling so that it start making its way to hit back up like that. Okay, so we spot out in any of the graphs we're looking at, there will always be a few of those special points where you got the function hits a peak where it stops rising, and then the function hits a valley. Okay, people call that peaks and valley. Right there, the function hits a peak and hits a valley. Sometimes even in my own terminology, maybe my own style of calling that. I see that as a high peak and low peak. Right here, high peak and bottom peak. Right there. Okay, it's indicating that the most it can go for the low and the most it can go for the high. Right there. And then so here we also got another point like that, where you can see that the function was rising. Now, no matter disregarding all of the bent crazy shape, but disregarding all of that, the function was rising and rising to that certain point, x equals c, for example. And then at that point, the function stops rising. Okay, so we recognized all of that nature right there. But then, so now, before we get even further into that, let me remind you one property. One important thing that we've learned. So we've learned this from long ago. Y equals f of x. Okay, so this is the function. This is the given function. And then we've learned taking the derivative throughout the whole time so far, all of that time prior to this point right here. Then we call that dy dx, right, as a notation for derivative. But basically that is our f prime of x. And then we So starting with a function, after taking the derivative, we've learned and hopefully have become fluent with the idea that the f prime of x itself is also, okay, a function of x. And so needless to say, that beginning function right here is the given function, right? And then be more precisely, the given function of x. So we're taking x as the input variable, and then the given function here is, we already know whatever function that is. But now I just want to emphasize taking the derivative, right? The general derivative we've been learning, and then that was the reason we gone through all of the crazy the derivative rules like that. But in the end, f prime that we have found throughout the quarter so far is also another function of x. And then the brief idea reminds you again that the reason that f prime of x is a function of x is because the whole purpose of getting f prime of x is to get slope of the tangent line. So you got a function, and so at a point right here, for example, at some point x, then you got the slope of the tangent being measured to be this high, okay, and maybe positive slope, whatever. And then when we switch to a different point, the slope of the tangent line, if we place a tangent line there, the slope of the tangent line is a different value. And that's why the slope of the tangent line changes depending on the value that we put for x. So we can call that at x0, at x1 here. And then at the different point value for x, at different value for x, we can call it x2. The slope value changes again. See? It's all about the tangent line, but now as we switch on the same function f of x, but as we switch to different x values, the slope value of the tangent line changes. And that's the reason why we came up with the idea of f prime of x being the general formula, some kind of general rule to determine the slope of the tangent line at any given x value. And so in the end, ultimately what I'm seeing is f prime of x itself is also a function of x. Okay, and so after some of those brief review like that, I want to mention a couple of things that you should have seen this back among some of your assignments that you've done long ago, but now it's time to really formalize all of that idea like that. But let me still retain the graph here a little bit, and so you can see that now f prime is also a function of x, and then of course that's related to the beginning function. So the beginning function was here, okay? And then I was talking about at different x values we can put a tangent line there, and the value for the slope of the tangent line changes depending on where we put the x value at, or depending where we put the tangent line at. And so now if you're observing a little more, just look at this picture right here. When I put the graph, right? When I put the graph here, when I put the x value here on the graph at a value where the tangent line here is just right in the picture, the tangent line is recognized to be a positive slope, right? And so at some point we may have f prime of x being positive. So let's say, or more specifically at x sub 0, here we got a positive slope, and so that means the derivative here has to be positive, okay? And then at some other point, if we recognize the nature of the function that's falling down like this, whereas for example at x2 right here, if you're substituting that into the function, and then we got a point, and right at that tangent point we put a tangent line, then we notice that at some point, right, the slope of the tangent line may turn out negative, being negative, okay? And then this guy right here, x1, the slope, the tangent line is still pointing up from the left to the right. So I can say that f prime of x1, okay, f prime of x1 is positive as well. Okay, so now here's what I have put this in some of your assignments in the past, but now it's time to really make that formal idea. But see, there's going to be some interval that no matter, we don't need to look at the precise point, but there's going to be some interval, say about here. From the left to the right on this graph right here, there's some interval where the graph of the slope of the tangent line is completely positive. See, I put a tangent line here, I put the tangent line here, or I put a tangent line here. It's all going to be a rising positive slope tangent line. See, rising. Whereas there's some other tangent line here where there's some interval where if you put a tangent line, it's going to be a negative falling tangent line like that. I hope you guys following with me on that. Okay, and so we had this kind of problem that I sort of prepped, giving you some preparation idea from a little while ago. And let me now bring that up, and we can make it formal right here. So we had this kind of problem a little while back. At that time, I left that assignment there for you guys to look at, sort of like for you to think creatively. But now let's think about it. So I just now precisely mentioned the function itself is a function. And of course, the derivative that we found is another function. So what we have here in this kind of problem here is a list of functions. So those original functions we have, those are in red ink, in the red color right here. So the f of x is the function in red line, and then any one of these is the derivative, the graph of the derivative as a function. So this is some derivative of some function, and then it's being regarded as a function. It has a graph here. So what we want to do is we want to match. Let's say with this graph right here, which one here is going to be showing the graph, and we have a list of 4 of them. Okay? So 4 functions with 4 graphs of derivatives. So which one here is showing the graph of the derivative of that specific one, for example? Okay, and so I left that as a something for you to creatively apply your idea. But now, what have we learned from that particular assignment? And that's what matters for us. And so in the way how I'm seeing that now. So we've talked about that the function is rising and going up, going down, right? And so I've been talking about positive slope. So now you can see through that picture an area like this. See, about the x equals a, if we place a tangent line there, we're going to reach a flat out tangent line. And then a tangent line like that, yes, specifically the derivative at x equals a has to equal 0. Because it's a horizontal slope tangent line. And then we're going to have the same behavior at those other points on this quick sketch that I've made right there. So at x equals b, we are going to have a horizontal tangent line. So that means the derivative has to be precisely equal to 0. F prime at b has to be precisely equal to 0 because we have another horizontal tangent line. And then here at x equals c, I spotted out, and like I said, I haven't shown you precisely, and even in that activity I brought up earlier, we haven't learned how to precisely identify those other than looking at the graph. And then we will learn to identify these more precisely later on. But then at x equals c, in the picture here, we have another point where the tangent line reaches horizontal slope. So horizontal slope or horizontal tangent line means the derivative equals 0 because it's 0 slope. So we got about 3 points on this graph right here having 0 slope tangent line, 0 slope tangent line, and 0 slope tangent line. Okay, so what about in this area? See, the function was rising, right? And so in the picture, if I place a tangent line, if this is my tangent line here, this little marker is my tangent line. If I place a tangent line here, I place a tangent line there, see, anywhere in this area, then here, in the way how we connect with what we've learned, in this area, anywhere, any x values, for any x value less than a, right? Or another way of saying before x equals a, then we got generally f prime of x has to be positive, okay? Because the function is doing this, going up and going up, or placing a tangent line anywhere here, we have to end up with a positive slope of tangent line. So that's the way how we see that's connecting with slope information. But now, from our pre-calculus understanding, or just by looking at the graph, another formal terminology is like this. You see, f prime of x is positive in this interval, okay? Anywhere before x equals a, or anywhere for x less than a, in this picture right here. But from looking at the graph from the left to the right, I was mentioning this a few times here, but the function values rising, rising, and rising, going up and going up, getting higher. So the precise term for that, I'm saying that the function is increasing because it's going up like that. So increasing is corresponding to increasing is or is increasing means that the slope of the tangent line is positive in an interval. Okay. All right. So we start using that term now. So in between x equals a and x equals b, these 2 points are special because we have tangent line hit the zero slope right here. Tangent line being horizontal. So we have seen from our picture, then in that case, if we place a tangent line there, we got negative slope, negative slope, negative slope, negative slope. Okay, so a tangent line geometrically has negative slope. Okay, so I'm putting in between x equals a and x equals b, the tangent line, or f prime in this area. Any f prime of x in this area has to be negative. That's how I'm seeing it. So I might have to write that to be along with the graph, so it's looking a little bit out of order. Hard to read right there. But now in a more formal term right here, see, the function goes from high, and by the time that we reach to b, it drops down low. So in that way, the function in this interval, the function is regarded as decreasing. Okay, the function is regarded as decreasing, and then yes, it's the value is falling just like that, from the left to the right. Okay, and once again, at that point specifically, the function is neither increasing nor decreasing because the function right there reaches a zero slope tangent line, or the function out there, if we place a tangent line, it hits a horizontal tangent line. Okay, so horizontal tangent line right at that point, right at that only one instance right here, then the function is neither increasing nor decreasing. Okay, so that's one thing to keep in mind right there. And so now let's continue. So in this picture, x equals b, right at that instance, x equals b, we reach a horizontal slope tangent line, horizontal tangent line, meaning zero slope. That's why I wrote it down right here. The slope of the tangent line has to be positive in this area. You place a tangent line here, it's a rising up, pointing up tangent line. You place a tangent line here, it's a positive slope tangent line. Place a tangent line here, anywhere between this interval from between b, x equals b and x equals c. Placing a tangent line there, we're going to have a positive slope tangent line. That's why f prime of x generally has to be positive in this interval. But in the way how it connects with the function, then the function is increasing in that interval. Okay? Increasing. And so in the way that's how it is. In the way it is, the function is increasing up to when it hits x equals c, the function stops rising right there and starts falling down after that. And so here I have here I have decreasing. The function is decreasing in this interval anywhere x greater than c, but then that means mathematically or as a derivative, the slope of the tangent line or the derivative value has to be negative in that area. All right. And so now I've been mentioning and hopefully making it real clear about increasing, decreasing, and all of that, the horizontal tangent line and horizontal tangent line and all of those. Okay. And so now we're making it formal. You see, the function was increasing, and then I use that term. It stops increasing, and then it starts turning it down, turning it way down right there. Okay, and so a point like that right here. Okay, we say that we have a, see right here, it hits a high point, but the high point happens at x equals a. So let me repeat that again. The function hits a high value, but the function hits a high value at x equals a. So the high value right here, I refer to that as a local maximum, right? And allow me to write that for short, just local max. Down here, at that low point, the function's output, the vertical value, the function hits a low value right here, and then it stops getting lower, it starts rising up right there. So I'm going to say that at this point, the function reaches a local minimum. And then my shorthand writing local min right here, indicating local minimum. Okay, there's local maximum, there's local minimum. Okay, and then it has local minimum at x equals b. Okay, and so same way right here, you can see that this point right here has to be called, that point right here, okay, has to be called a local maximum again. Okay, a local maximum and local minimum. And so we start getting into that idea. So now before we get too far, let's formally write down a couple of definitions. So now as a formal definition, and my board space is getting extremely tight right here, so I may have to write pretty small right here, but a function, so number one, right, so we now Because just now on the board I was defining I was using the term the local maximum and the local minimum. So now let's give a formal definition before we can work more formally with that. So a function f of x is said to have so the term I use here, local maximum. Okay, a local maximum at, so local maximum, but specifically given at some given point at a value x equals a, for example. So back on my picture, I was using it at x equals a. The function reaches a local maximum. So the value right here, the vertical value hits its max, the highest it can go. Hear my term on that. But it hits the highest vertical value at x equals a. And so that's why, in the way how we're saying it, the function is said to have a local maximum, okay, at the given value x equals a. Okay, but then that happens if it satisfies the following. I did not mention this in the picture, but now it's time to mathematically mention it. It means f of x is less than or equal to f of a. But then for all x values that's not a in an interval around x equals a. Okay, so here's how it means. Here's what it means right here. You see, when x equals a, the function f of a is going to hit its highest, and then anywhere else x not a means this some point here, some point here, some point there, some point here. X not equals a. So for any other x value not equals a, the function value is lower than that height. So that height here is the highest. Okay, and then anywhere else x other than a, anywhere else is just lower than that point. And that's what it means. But now be careful with my wording a little bit. In an interval around x equals a, and to be more precise, around here I mean close enough, just nearby. Okay, the word around right here means an interval nearby x equals a. This is what it means right here. See, think about x equals a right here. If we pick an interval that's way too far, because anywhere outside of a, anywhere other than a, then we have an interval can be that large. But an interval that large may include some other local maximum. So we don't want to get things like that. We just want to get some interval that's just right around a. And so this is the part where it starts going a little loose here, because for our level here at Calculus 1, and it's hard to define, it's hard to come up with the right now at this instant, it's hard to come up with how close is considered as a nearby interval. And so you just rely on the picture over here, but at least you can see that right around a, in some interval about right there, right? In some interval about right there, then any others, for any x value, see an x value here, an x value here, it's all x not equals a. The function value, see, it's lower than that. The function value here, substituted into the function, is lower, right, than that maximum f of x. And then in the next few days, in the next few lectures, we should be able to detect where precisely is that nearby interval. Just right now that it's going a little loose like that in the way how we explain it. Okay? But so that's how we define the local maximum. And so similarly, number 2, a different definition here. So one definition, but I'm doing for both. So a function f of x is said to have a local minimum. A local minimum at some other value, x equals b, for example. That's sort of like from the picture that we've seen right there. Okay? If the function value, any other function value here has to be greater than or equal to f of b. See, for all. So this symbol, in case I haven't mentioned it for you guys, it's the upside down letter A right here, but it means for all. So for all x values, that's not b, in an interval around, but around here it really means nearby. Okay? And we will learn how to find a precisely detect how nearby that interval will be later on in the quarter. X equals b. Okay? So that's what it means formally by what a local maximum is, what a local minimum is. Okay? So go ahead and spend some time writing it down like that. But so in this picture right here, again, I was talking about increasing has some correspondence with the derivative being a positive. Decreasing, so if there's an interval, right, the function is recognized to be decreasing. That means it's connecting with the derivative as the derivative has to come out being a negative value. So increasing means the derivative of the function is positive. Decreasing means the derivative of the function has to be negative, like that. So we actually formulate a theorem at this point. Okay, so let's look at the theorem right here. A function f of x, okay, is so number one, the function is increasing. Right, so the term I was using on that picture earlier. So a function f of x is increasing in an interval from a to b. So let's quickly look back at that picture again. I mean, at some pictures similar, but increasing is kind of like this. See, the way how I'm drawing it, the left to the right, right? The function keep getting higher vertically. So let's say you have an interval from a, right here, x equals a, and x equals b, and that's what the interval is here is all about. And now increasing or decreasing, we have to be talking about strictly inside an interval. So in that way, I'm using the parentheses here instead of the brackets for closed interval. So this is an open interval. But see, increasing means what? The derivative has to be positive here. Okay. So now we're formulating that into the theorem. So the function f of x is increasing, right? If the derivative of the function is positive, okay. So that means every behavior is taking inside of that given interval. So in between that interval, if you can prove or show that the derivative of the function is positive, then it means the function is increasing. Okay, that's how it is. And so similarly, we can have a function is decreasing in some given interval from a to b if the derivative is found to be negative or proven to be negative. The picture is similar again. I can bring up a similar picture. See, it can go like that. Okay, there's an interval between a and b. Okay, then see, anywhere that you place a tangent line here, anywhere here, see, it's going to be negative slope tangent line. And so if you can prove that generally anywhere inside, if we can show that anywhere inside of that interval and placing a tangent line here, it's going to have a negative tangent line, a negative slope tangent line, that means the function is said to be decreasing. Okay, and that this theorem here makes connection and formally makes the connection between the derivative value that comes out to connect with increasing or decreasing. And increasing or decreasing here is a term that we actually learned from pre-calculus. It's indicating graphically that the function is dropping vertically. That's decreasing. So that's how we understand about increasing or decreasing. And then increasing means the function is gaining its height right here from the left to the right. But now, see, the theorem comes in and says, hey, connecting that with derivative. When derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. Okay, so this was that theorem that we wrote down at the end of the lecture earlier, right? And so, then that graph that I brought in, graph went up, went down, right? So at some x equals a here, for example, we have a horizontal tangent line. So horizontal tangent line means what? It's the slope 0 for that tangent line, right? So your f prime has to be f prime precisely at x equals a has to equal 0. Well, I'm saying that. And then so I've been spending time explaining that. So in that interval anywhere before getting to x equals a right here, the function, we notice the function is rising up, right? Going up here. So it's increasing. That's how we're calling it. That's how we're viewing it. Right? But then that means the derivative, we place a tangent line anywhere on this area of the function. The derivative is positive, just like how the theorem was stating it. And then just like that, there's another value right here. I call that as a bottom peak, right? Or maybe more commonly people refer to that as a valley. So peak and valleys again, right? But see, we have at that particular instant, we reach another flat out tangent line again, right? Horizontal tangent line. Or another way of saying it's mathematically f prime at b here equals 0. It's the slope of the tangent line there, right? It's 0 slope. And then we have another one, right? Right here at some other value, x equals c. Well, so these are all those places where you're looking at those points, the derivative at the value right there equals 0. Right? And so now in that way, and so see, that's between those values again, between those values that we're giving a horizontal tangent, and of course the function is either increasing or decreasing. So in this area right here, the function, and I'm having a hard time redrawing it right here, but the function is decreasing right there, right? And that means that in this area, in this interval between a and b right here, then the derivative, according to the theorem, right? Negative. And then between that interval over here, the function, see, from the left to the right, right? The function is rising, getting higher and getting higher. You guys follow with that? Okay? So once again, the way how we see it, we call it, hey, the function is increasing, right? The way how we view the function from the left to the right. But then mathematically now at our level, we've learned about derivative. The connection now is that the derivative has to be positive in that interval. So you place a tangent line here, you place a tangent line there, the tangent line is always pointing up. You guys notice that? Okay? And then again, if there's whatever outside of that interval right here, we notice another decreasing right here, right? Another decreasing. And yes, f prime is negative anywhere passing the x equals c again. But now we want to give a, because I keep mentioning about these special points that giving horizontal tangent, right? The slope of the tangent line being precisely 0, but only at those instants. Right? So, but we don't want to keep calling that, the point that give the horizontal tangent line is way too long, right? So we come up with another definition right here. All right, so now I'm going to go ahead and add in another definition right on this board right here. So that's my shorthand writing for what a definition is. So a function f x is said to have a critical value at x equals a if one of the following happens. Now, if the derivative of a equals 0, that's one of it, or so any one of the following requirements here is enough to say that the function has a critical value right at that point. F prime of a is undefined. I should have put or. Right? So we only need as long as one of the requirements here, one of the criteria here is met. Right? Then that means the function has a critical value at that given value x equals a. And so a definition is a way to name something. A definition is a way to name something. So we just now give a name what it means by being called a critical value. Right? So now look right into this quick sketch I made right here. So some function f of x, and we spotted right from this picture over here at x equals a, we have a horizontal tangent, right? Or the derivative of the function at a equals 0 right there. So now I can now legally say x equals a right here. I'm saying that we have x equals a is a critical point. It's a critical value. You guys follow it? Right? And then we have spotted out another critical value right here. So this critical value, this is another critical value. And that is also another critical value. We have spotted 3 critical values. So at any of the x, at any of the values, any x value on the x-axis giving a horizontal tangent, right? Either a horizontal tangent or an undefined derivative, we call that x value a critical value. And so there could be times where, see, what's up with the undefined? See, there could be times where your derivative, your function goes like this. Sharp angles again, remember? Okay. So right there at a value like that, right? X equals a. Namely, we're saying that f prime of a, right, in that situation right here is undefined. See what I'm saying up? Okay. And so now as being undefined for the derivative, so now we call x equals a right here a critical value. Okay. That's another way of recognizing or spotting out a critical value with it. So and these two properties will not happen at the same time. So either it's a zero slope, right, at that point, or being undefined. But there's no such thing as zero slope and being undefined at the same time. Okay, so be aware of that. All right. So now after giving that definition, formally what it means by being a critical value, let me retain that information. I'm going to erase the board here, and then we're going to bring in the first example. And I've been spending a lot of time looking at increasing and decreasing and critical value. And our topic title right now is talking about the maximum and minimum value, and we didn't even get into that yet, right? Because we're still building up the little pieces of information. So the one I have right now, let's say F1. Find all critical values of f of x. Now to get started into the problem, we are asked to find the critical value. So what does it mean by critical value? The critical value happens if f prime of a, right, equals 0 or f prime of a is undefined. But anyway, it's heavily dependent on the derivative. See what I'm saying? Huh? Okay. So in order to find the critical values, or all of them, we've got to find our derivative of the function. So f prime of x, right? Well, at our level at this point right now, then this should be easy, right? So that's making it 4x cubed minus 12x squared. You guys following? So we found the f prime. And so any critical values that we can find is going to be those values for x that's making either the f prime equals 0, right, or f prime undefined. Well, so that's what it means by finding all critical values. So any critical value we're about to find, once again, I repeat, right? Any critical value we're about to find is going to be those x values either making this f prime here equal 0 or making f prime here undefined. Sounds good? There are two possibilities may happen, right? But now let me point out this truth here for you guys. See, the f prime of x that we're looking at right here, f of x that we have found right here is a polynomial, right? You guys agree? And so being a polynomial that leads to f prime of x is defined, meaning we can have a value for all x values, right? At every x value. You guys with me right there? Right. What's important about that statement that I was indicating? The statement just now guarantees that, you see, in order to detect critical value, once again, we rely on f prime of a equals 0 or f prime of a is undefined, right? But just now, with that statement right here, I ruled out this possibility. Okay, our f prime here is a polynomial function, so there's no way that it's going to be undefined anywhere. See what I'm saying now? So it's sort of like we roll down some possibilities and we narrow ourselves down to the only possibility left is some x value may cause the derivative equals 0. Got the idea? Okay, so now we're going to tackle that now. Okay, so now that means the only choice left for us. Let's set f prime of x to equal 0 here, right? Because once again, critical values aside from those being undefined that we already ruled out, right? Then the only choice, the only possibility is left. F prime of x may equal 0 at some point. So setting f prime of x equals 0 over here, then that means what we lead to producing 4x cubed minus 12x squared to equal 0. You guys always agree on that? And now we have produced for ourselves the equation to solve for it, right? The equation to solve for x. X is the unknown. Okay? And then with this equation, we can easily, I mean, there are quite a few different ways right here, but the most common method is to factor out. Okay? I mean, after setting the opposite side being 0 over here, all terms here, I recognize the common factor, so I'm going to factor out 4x squared. You guys repeat that? Right? And now we're looking at x minus 3 equals 0. Right? So I was just now factoring out the left-hand side, the side that's opposite from 0. Now see, we purposely left. X equals that. So now with that equation, what are the solutions? You see, now we're looking at x squared as 4x squared as one factor of the product, right? We can set that equal to 0. That's one equation. Okay. And then the x minus 3, another factor in our entire product right here, we can set that equal to 0, right? It's not like anything new here, right? It's things that you've seen back in your pre-calculus 1, right? And so now x minus 3 equals 0 simply come out by adding 3 to both sides, right? Making it x equals 3. You guys agree? Okay. And then for the other one right here, we can divide both sides by 4, making it x squared equals 0, right? And then we take the square root both sides again. So that leads to, right? That leads to x equals 0. So we found really 2 critical values, right? The values that we found here, again, these are the values that cause the derivative to equal 0. Those are the unknown values that making the derivative equal 0. And that's why we have found those, and these are all of the critical values that we have found. Right? We keep getting closer and closer to our goal, learning about how we can find the maximum and minimum value. So I talked about decreasing, the increasing, right? And I talked about what the critical value is. Okay? So let me now introduce for you guys another theorem. The definition for critical value is still here. The picture I had to erase on the other board, but I can remind you guys again. You can see there's your function may be going up and down, right? There's up and there's down, hit you a low and hit you another high again, right? So these are points right here are now what we so-called some x equals a, some x equals b, right? And some x equals c right here. But one common characteristic of these points that I spotted out, they have 0 slope, tangent line right there. You guys follow it? Right? And then we call them formally with a name. These are the critical values, right? And then we did the example just now to be able to find those. So now the theorem here is stating that, I mean, the observation is right here. At some critical value, our function hits a max, right? See that there? Okay. And now precisely speaking, this max right here, according to the definition we have already learned, this is a local maximum. See what I'm doing there? Okay. And then that point right here, now we call it, according to the picture, we call it as a local minimum, right? But it happens at a critical value. So local maximum or local minimum or any other local maximum, they all happen at a critical value. See what I'm saying there? Okay. This guy right here is local maximum. Right. That guy right here is local minimum. So now we're formulating a theorem. Here's how the theorem is saying. If f of x, right, has a local maximum, right, or local minimum, either one of those, right, at a given point x equals a, okay, then in that way x equals a, right, must be a critical value of f of x. So the picture was illustrating that idea earlier. And it's just me, it's my own habit. I didn't get out of that yet, but anytime I draw a critical value, I tend to stay with those critical values where it has 0 slope, tangent line like that. But remember, critical value can also be those x values making your derivative undefined, right? So think about those sharp angles. So is it still consistent with the theorem? Think about you have a graph that goes like this, up and down, but then hits like a down and then hits up and then turn like that. See what I mean? So you got the critical value here, 0 slope, tangent line, 0 slope, tangent line, but here you have an undefined like that, right? So those critical values, you're still gonna obtain, you're still gonna reach to maximum, local maximum here. It's still considered as a local maximum. Okay. And so of course local maximum and local minimum here. So that's why, once again, more generally speaking, right? Anytime your function hits a maximum or hits a minimum, that point right there has to be a critical value. Right? Either it's in that case of a critical value being undefined for your derivative, or it's a critical value being a 0 slope for your derivative. Zero value for your derivative. Right? You want to find all local maximum, right? F of x equals x to the 4th minus 4x cubed. And as a matter of fact, let me correct my wording a little bit. These things should read precisely local maxima and local minima. You see, so why not maximum? Why does it have to be maxima? Because we're talking about this is the plural of maximum right here. Because there can be multiple high peaks. Yeah. See what I'm saying? So locally speaking, there can be multiple of those high peaks. That's why it's maxima. Because maximum refers to only one. Okay. And in the same way over here, local minima, we may find multiple low value right there, right? And so that's why it can be plural. So minima is the plural of minimum right there. Okay. So when you're looking at specifically one minimum value, and when you're talking about just that one particular minimum, then you say, hey, that's the one of the local minimum. But now we're talking about finding all minima like that, right? Then we're using that term, right? But now, so how can we apply the theorem we've learned? The function has a local maximum or a minimum. If the function has a local maximum and a local minimum at a given point, if we can spot it out, then that means those values has to be the critical value. And so now think about it. We can apply this understanding into the real work right here. So now if you want to find the local maxima and the local minima, the first thing is to detect all critical values. That's the first big step. Okay? We're going to have to detect all the critical values because the way how it is, the local maximum or the local minimum has to happen on those critical values. So we got to narrow down all the critical values first. And then that's where, if we spot out any maximum, minimum, it has to be among those critical values. And so now, right on this problem, I purposely use that the same function from the earlier example so that we can save some effort here. So now you can say that from example 1 that we've done previously, right? That we found x equals 0 and x equals 3, right? Or critical values, and these are all we have. So everybody is clear with me on that, okay? All right, but now the problem here is that after we have detected the critical values, any one of these critical values can produce a max or a min, right? Because we haven't seen the graph yet. You see what I'm saying? No? We have not seen the graph. So because a critical value is only simply telling you that we have a horizontal tangent like that, but it could be a horizontal tangent at the high or a horizontal tangent at the low. Like that. Right? So being a critical value is not enough to tell whether we're having a maximum or a minimum. And so now we're going to have to detect that even a little further. I'm going to get back to this board over here. But now, let me come into this picture over here. Okay, so that is a critical value. That is also a critical value, and that is a critical value, right? So any critical value, just like what I said earlier, could be a maximum or it could be a minimum. But now how can I detect? So let's say for this local maximum right here, the way how it looks, it has to be that the function is increasing before getting to x equals a, right? So before x equals a, the function is increasing, then the function decreasing, and then the function is flat out right at that point. You guys will be on that, okay? Okay, so that gives the criteria. See, so we have to detect the increasing and the decreasing interval. So that, if the function is increasing then decreasing, then that point in the middle over here, that point in between has to be, that critical value in between has to be a local max. And then likewise, the function here, if the function is decreasing then increasing, right? Of course, there's a critical value in between, right? But that critical value there has to be a local minimum, right? And so now that gives us some plan here. So the plan here is how we go. This is how we go. The formal technique here is called the first derivative test. Okay? So it's still in this example right here, but the technique being brought in right here is called the first derivative test. But the idea is now that we're going to use a first derivative. And then I should also mention, from example 1, we got these are critical values, right? And f prime of x, right, was found from example 1 being 4x cubed minus 12x squared. You guys all agree? And we even, as part of the solving work, we even factor out this derivative. You guys remember? So I factor that as 4x squared, right, in parentheses x minus 3. You guys will need that. So it's just the factor form of that derivative is the 4x squared times x minus 3. Right? I mentioned that now for a reason. So here's the idea of the derivative test. We're going to use the derivative to detect the increasing and the decreasing interval. And remember, increasing means what? The derivative has to be positive in an interval, right? And decreasing means the function has to be negative. The derivative has to be negative in an interval. And so the whole idea about the first derivative test is that we actually going to construct what's so-called a sign chart. Right? So we're going to build a sign chart. All critical values that we have found from example 1 here on the same function. From example 1, we already found critical values 0 and 3. So just think about the sign chart here, just the line of numbers here. Just the line of numbers. So if we put down the critical value 0 somewhere, and then 3 has to be to the right-hand side, right? Just the way how we put numbers on the line, that we go increasingly from the left to the right. So now, in that way, after putting down the 2 critical values, or putting down all critical values, for this problem, we have broken the whole line of numbers into 3 separate intervals, right? There's one interval over here. This interval over here is indicating x values anywhere between 0 and 3. You guys follow it? Right? That interval anywhere here on the left-hand side of 0 refer to those values x less than 0, right? And then this interval over here refers to those interval where x is greater than 3. Right? Those we got. So after just simply the way how it is, after we put down all critical values, we have naturally broken down the entire line of numbers into 3 separate intervals for our problem. And so now here's the sign chart. Here I'm going to do the following. See, this is the interval of x, interval of x, interval of x. But I'm going to check for it's called the first derivative. So I'm going to check the sign of our first derivative. See what I'm saying? That's why it's called a sign chart, because I'm about to build a chart that's, focusing right on the 3 separate intervals here. So for the first interval on my chart here, first interval, x value is less than 0. Why don't you guys pick a value x less than 0? Pick one on your own. Negative 1? Okay. So you pick negative 1. See what I mean? So negative 1 here, we use a first derivative test, meaning I'm going to substitute that chosen value into the first derivative. So you guys would need that? Okay. Now, there's a good usefulness of using the factor formula here, because here's the thing, here's how I'm seeing it. With negative 1 being your chosen x value in that interval, right? When you substitute this into we have 4 as a positive, right? Times some negative 1 squared. See what I'm saying? Huh? Right? And then times negative 1 minus 3. You guys will need that still? So I'm not going to be really too worried about the final value. I'm not really worried about the final value. I'm worried about the final sign. These are going to be, after this product right here, after multiplying all of that, right? After substituting in x equals negative 1, am I getting a negative sign of the derivative or not? See what I'm saying there? And it's easy to tell. Negative 1 after square being a positive, right? Positive times a positive, making positive, but then here's we got the negative. That's why the overall answer here has to be what? So the sign of your derivative in this interval has to be a negative sign. Now you guys follow it with that, okay? Sometimes professors introduce that at pre-calculus 1, not for derivative. The sign chart has more purpose in that than just that. Okay. But so you guys haven't seen it at all? Okay, love it. And here you go. We formally use it here. So now here's the thing. So now that you know in this interval x less than 0, the derivative will turn out negative, right? We only used one test point and it tells you the entire story. Okay? So she gave me x equals negative 1. You could have chosen x equals negative 2. It should come out exactly the same result, because all I care is the sign of the derivative. So now the sign of the derivative being negative means the function, if you put it in the graph, if you putting up the graph, the function has to be from the left to the right, decreasing. Are you seeing that there? I'm drawing an arrow that's kind of like slanted, right? Pointing down from the left to the right here. It's indicating decreasing. Because we had a theorem earlier saying that, hey, if the function is decreasing, right? I mean, the function is said to be decreasing if the derivative is negative. So just now we found out that the derivative in that interval is negative, right? So the function has to be decreasing in that interval. You guys good with me on that? So the sign chart here, check for the sign of the derivative. It also tells the behavior of the actual function in terms of increasing or decreasing. That's why we call it as the first derivative test. So now let's move on to the middle interval. Because we got 3 separate intervals, right? 3 separate zones right here. So pick a value between 0 and 3. You definitely don't want to pick x equals 0 and x equals 3. We want exactly between, right? Somewhere between 0 and 3. Pick one. 1, x equals 1. There you go. So that's your test point, right? X equals 1. And it falls inside that interval. And somebody else can choose a different one, like a 1.5 or like a x equals 2. It works too. I'm going to substitute that test value, right, into the derivative. The factor form is the more preferred one. See what I'm saying? Because it's easier to calculate. Here's how I'm seeing it. 4 times 1 squared, you guys following? Right? Times 1 minus 3, right? So that's positive, times a positive, times a negative, right? So your overall, so the sign for your derivative in this interval has to also be another negative. You guys need that? So that means the function is still decreasing in that interval between 0 and 3 for x. And then so now this last interval over here, pick a test point. 4, yeah? 4 or 5, anything greater than 3. X equals 4, right? Substituting that into your derivative. The factor form is the more preferred one. So 4 times, right? 4 squared. We got 4 minus 3, right? This time we got positive times positive, right? Times with a positive. Your overall signs of the derivative in this interval is a positive sign. We looked at that. So that means the function will be increasing in this interval. Sounds good? Okay, so here's how we're putting it, the pieces together. Remember, at x equals 0, it's a critical value, horizontal tangent line. At x equals 3, it's another critical value, horizontal tangent line, flat out. So you now realize, see, the function was decreasing, right? And then rising back up for here. What do you say about this x, this critical value, x equals 3? It has to be a local minimum. See that there? Because anytime your critical value stays exactly in between the two behaviors, decreasing then increasing, right? And that critical value has to be a minimum. And then anytime that your critical value stays between increasing then decreasing, and that critical value has to be a max. And more precisely, we call them the local max or local min. See what I'm saying? That. What about this guy right here? It was also a critical value, but it's not exactly between some two opposite behaviors, right? It's going decreasing and continue to decrease. So this one here is neither. Get it done? Because like I said earlier, a critical value can be a maximum or a minimum or neither. I mean, maybe I forgot to say or neither earlier, but you see, it could have been even one of the two, or sometimes it fails both. Right? So now we found. So all local maximum, local minimum, we only found one local minimum here, right? And then there's no local maximum in this problem. Okay? And so now the way how we're stating it, formally stating it, we're saying that f of x, right? This function over here has a local minimum. You know, we're pretty guaranteed that there's only one, right? It has a local minimum at x equals 3. But then that statement right there is only saying that, hey, this is where we can find, right? Where we can find a local minimum. Okay, so let me repeat this statement here. After our work with you, we're saying that f of x has a local minimum at x equals 3. That's one statement. But this statement only guarantees where we have spotted the lowest point, where we have spotted the lowest value right there. But then how low does it hit? How low does it hit? Then we're going to have to answer the local minimum value, right? To get that local minimum value, what do? We substitute the critical value x equals 3 into the function. Okay? And so f of 3 right now, and I mean, we substitute actually the critical value into the function. Otherwise, substituting this into the derivative, it's going to come out 0. That's not what we want, right? So we're substituting the critical value into the function. And that's going to give us the minimum. value because we have already decided that hey, at x equals 3, right, we detected that we reached a local minimum. So now we just want to find out, yes, we know we reached the local minimum, but how low does it hit here? That is the answer. So 3, to the 4th power, right, minus 4 times 3 cubed. So that's making it altogether a negative 27, right? Okay, so negative 27 is the local minimum value, okay, how low it hits there. That's always, think about, a lot of times when you're asking people, hey, where's the tallest building on the planet, right there? That question is different with how tall is that building, right? So if I'm asking, hey, where's the tallest building in the world, you're probably going to point to, hey, the World Trade Center that's the building collapsed. Okay? Or you may point out, hey, that currently that's the tallest building on the planet is now somewhere in the world right there, but that's where we find the tallest value, the highest value or the lowest value. But then now once we know what it is, when we came there, we want to know how high does it hit, right? Or how low does it reach again. Okay? That's why anytime we're answering a maximum or minimum value problem, there are always 2 things to answer. You have to answer where you found it, right? Where you found it, and how low or how high does it hit. Right? It's sort of like a dual nature of that question like that. And the wording itself is making, you see, when you're looking at the wording, that wording right here, very brief, but that's where it's bringing in, you have to bring in all of that, the explanation right there. So we want to find all local maxima and minima, but that's it. It didn't ask for where to find it, and so it's your responsibility to find out where we find it, and then how low or how high it hits. Yeah. Right. So in a simple instruction, but a lot of time it means that you have to do a lot of work. Yeah. Simple instruction means a lot of work, very inclusive level of work. And then we're not quite done with this particular problem yet. So as far as the maximum, do we spotted any? Have we spotted any? We haven't, right? And so now I get to say no local maximum. Okay? And so by saying no local maximum, then we don't have to bother with finding out how low or how high it is. Because there isn't one. So now let me give you guys a quick graphical illustration of that problem. Okay, so here's the blank graphing space right here, and the function I've had on the example. Let's now put in the actual graph. You guys see the graph that just now popped out? Yeah. Okay. It hits down so far to the point that I have to really zoom out a lot, right? But now think about this picture right here. The result is here. You see that waterfall nature right there? Okay. So that waterfall nature is indicating we do have a zero slope tangent line right there, right? If you place a tangent line right there, you do have a zero slope tangent line. But that tangent line, at that zero slope tangent line, at that critical value, the function was decreasing from the left to the right, right? Decreasing and continue to decrease. That's why at that critical value we decided that, hey, it was neither a maximum or a minimum. Okay? But then at the other value, it's about 3 right here. We hit a real low right here, right? So we have x equals 3, another critical value, flat out tangent line right there, right? Zero slope tangent line. See, and the function was falling down to hit that bottom low right there, trying to hit that real value and then swing back up right there. So that's why x equals 3 right here is a critical value, but further, that's where we found a local minimum. Right? And then see, that's just where, right, on the x-axis, where we found that local minimum at x equals 3. But then how low does it hit? See, negative 27. Right? That's why there were always those 2 questions. Yes?
So would we write the minimum value as a coordinate point, like negative 3, or I mean 3, negative 27?
Yes. It's a yes or no. So some instructor okay with that. But I guess for me, I want to be more precise in that. So I want you to answer, hey, at x equals 3, right? You reach the minimum, okay? But then how low it hits, calculate the value more specifically. But just simply giving me the point there is a little too brief. Okay? That's just how I feel. All right. So the example 2 that we've done earlier, sort of like broken it, a one big process into 2 steps right there. So now we're going to combine it into one bigger example. So let's go ahead and spend some time writing this down right here. So similar to example 2, but we want to find all, okay, underline that, all local maxima and local minima. F of x, 7x cubed minus 189x. Okay, so go ahead and take some time writing it down like that. And so just to let you know, before we start with this problem, go ahead and have your calculators ready because we need to do a lot of calculations. All right, so this example here is like example 2 that we've done earlier, in the sense that yes, we got a function given and we are instructed to find all local maxima and all local minima here for the problem. But now the idea is this function here is completely from scratch. So in example 2, I used the function that we already did, and we already found critical value from example 1. So example 2 went a little easier. But now this problem here, think about it, it's that one big problem where we have to invent everything from scratch. And so now sort of like the big step right here, we got to find the critical values. So as far as the critical values right here, okay, that's just one major steps that we're about to find, and we right now, as it's just a goal, that's just a plan for the work right here, so we may run out into only one critical value or multiple, so that's why I put plural here as optional, but that's what we're about to do. So we need f prime, okay? And now, like I said again, our function here, we're starting out completely from scratch. So taking the derivative for this function here, it's giving me 21 x squared, right, minus 189x. Yes, because there's no x here. Yeah, that's right. So the derivative here is 21x squared, right, minus 189. That's good. And so we factor out, and that's making it just 21, right? And then here we're looking at x squared minus 9. But see, so now x squared minus 9 takes us into a different style of factoring, right? We're going to end up with the 2 factors as well. As a matter of fact, 21 and then x minus 3 and then x plus 3. Okay? You guys all agree with me on that, because this is a difference of 2 squares, right? And hopefully I don't have to remind you too much into the algebra there. All right, so factoring here is just one step. Normally we don't have to do, but here it's just a one step that because in the next the step still in the same big stage here. In the next step, we're going to have to find the critical value by solving for equation. That's why being able to factor is a better idea. But simply just finding the derivative, and we're done right there. All right, and so now for critical value, we're going to set f prime, right, of x equal to 0. And I should have made that argument again. Well, let me just go ahead and finish with that. Now, so why are we only, remember, critical value is defined to be those x values where your function, our function here, is either undefined or being equal to 0. And so I made that argument in the earlier examples that the derivative we have here is a, see, f prime of x, right, is a polynomial. Okay? So being a polynomial, what's important about that is that it leads to f prime, right, is defined everywhere. That same argument. And so now based on the definition of critical values, then we have ruled out that possibility. So there's no, we won't find any x values making our first derivative here undefined. And so that takes away that possibility. So now we only need to, in order to find the critical values, we only need to set f prime of x, right, equal to 0. Okay. And so now setting f prime of x equals 0 leads to 21 x squared, right, minus 189 equal to 0. That's right at start there. And then this equation, now that we're about to solve, according to our optional work I've done earlier, Okay, because sooner or later we're gonna, most of the time we use that method to solve, right? 21 and then the x minus 3, x plus 3 here to equal 0. And you guys have to understand my intention is that now if it just simply this equation, if it just simply, after setting f prime equals 0 and we run into an equation, this equation here specifically in our problem is simply a quadratic, so you don't always have to factor. So factoring here is just one way. But the reason I kind of got you guys more further into the factoring route, okay, being able to factor, because there could be times that your derivative comes out being some polynomial higher degree than 2, right? For like a cubic or like a quad or a fourth degree or something like that. And so in that case, right there, when the equation that you're solving is higher than degree 2, then solving for that using factoring is pretty much the only choice, right there. Okay, so keep that in mind. So be ready, be able to factor, and factor will also bring in other good usefulness. So now with this right here, we're going to end up with two critical values, right? We're going to end up with x equals plus and minus 3. So my board is short, so allow me to just write it like that. Okay, x equals 3 comes out from that. X equals negative 3 comes out from that. So in the end, the critical values that we found is x equals plus minus 3. So we got two critical values. And I don't even know why I put that in a box right there, but that shouldn't be needed. Okay, so now we got the critical values. After finding the critical values, any one of the critical values could be a local maximum, a local minimum, or neither. We've learned that through the earlier examples. So for that reason, we're going to have to use the first derivative test right here. Using the first derivative test, and yesterday, in the earlier example, I was writing that down. First derivative test. That's just for you to understand what that is. But now the major idea is we get into the sign chart. Okay, we're going to construct a sign chart. And then this is just optional for you to understand. This is where we beginning with the first derivative test, right? But you don't always have to write this. So the sign chart here, once again, there's a line. We think about a line of numbers, right? We got only two critical values. One of them is negative 3. And then once you put that down, the other guy has to be 3. And after putting down your two critical values, then we have broken our entire line of numbers into 3 separate intervals again. Okay? That's just the line of numbers. And so now we have 3 separate intervals, and then we're going to build a chart. Okay. All right, so this interval here, we're looking at those x values being less than negative 3. The interval in between here, yes, the way how it looks, we're looking at those x values anywhere between negative 3 and 3. And then in this interval right here, it's where x values greater than 3 right here. Okay? And so now we're going to just simply, the way how we run the sign chart, and the idea recall from example 2, right? We check the sign of your derivative, not the sign of the function. And so anyone would like to give me a test point for this interval?
Negative 4.
Negative 4. So negative 4 will work just fine. So I'm going to test with x equals negative 4, right? So that test point that we have chosen right here now into the function. So quick calculation right here into the derivative. So f prime of negative 4, try the way we run it. And see, the factoring is again more advantageous right here. Minus 4, minus 3, and then minus 4 plus 3. That's making it easier because really all I care is the final sign of your derivative. So 21 here is a positive. Okay. Negative 4 minus negative 3 is a negative. And then negative 4 plus 3 is another negative. So positive times negative, our final sign. So in this interval, what it says here is that our derivative is positive sign in that interval. So we use one test point, but if you choose another test point, if you chose a different test point, it's going to come out the same sign result. Like that. So this is the sign of our f prime in that interval. It's positive. Okay. And then how about now we're going to advance to the next one. Anyone would like to choose for me a test point in here?
0.
1, yeah, 1 works. x equals 1, right? And that's just one test point. And I also heard someone whisper 0. That works too, as long as the value that you choose sits in that interval. And then, so once again, I'm going to substitute that into our f prime. So f prime of 1 here. 21, positive number, 1 minus 3, 1 plus 3. Okay? And so once again, you can see that there's a good advantage of using the factor formula. And so 21 here is a positive sign, clearly. And then 1 minus 3 is a negative sign. Okay? That I'm not too particularly worried about the actual value, because all I need here to worry is just the sign. 1 plus 3 this time is a positive. Okay? So now in the end, that means what? In this interval, that for any x values between negative 3 and 1, I mean negative 3 and 3 right here, then the sign of our derivative would come out being negative. Okay. All right. And so now the last one right here. Anyone would like to pick a test point for me on that interval?
4.
Right. 4 is perfectly good. Okay. So we go f prime of 4. That gives me 21 as a factor. 4 minus 3. 4 plus 3. Right? And this time it's positive sign for the 21 in product with a positive sign for the 4 minus 3. And it's another positive sign for the 4 plus 3 right there. So once again, being able to factor down your derivative is a good skill for this kind of problem right here. So it's positive all multiplied together. All positives multiplied together gives me a final sign being positive. So what it says now, our derivative is positive in that interval, anywhere x greater than 3. So these are only test points, right? These are just test points. I chose these that you guys gave me, but you guys could have done different values as well. Anyone learning here? Okay. But so now what it means is that after checking out the sign, after checking the signs of our derivative on the same chart, I'm going to produce another row, right? So that means now our function in this interval, anywhere less than negative 3, the function is, this positive sign is indicating increasing. And we learned that from the theorem that we learned earlier. We found out about that result right there. So now it's decreasing here. And that's what the way I'm drawing the function. I mean, drawing the arrow right there. See, the arrow is showing from the left to the right, dropping. So that's indicating decreasing. The arrow here is from the left to the right, is pointing, going up. So that's showing increasing. And then here it's increasing again. And so now we have a cleared decision now. At this critical value, x equals negative 3, at that critical value, what do we have to decide about this critical value? We must reach a local maximum, right? And then at this critical value right here, we must reach a local minimum. Because once again, in the way how I explained that from the earlier problems we have done right here, and from the major idea, see, anytime at a critical value, anytime that we have a switch between increasing then decreasing, then that critical value must be a local maximum. And then at any critical value where we have a decreasing then switch to an increasing, that critical value in between has to be a local minimum. Okay, and then we also saw that in the earlier examples that there's going to be some cases where it's a neither, right? And so now we have found. So now I'm writing my final statement right here. So f of x, right, has a local maximum at x equals negative 3. So we nailed down where we found a local maximum. But then the problem allowed me to remind you about the wording right here. The wording is dangerously asking for just find all local maxima and all local minima. Meaning, after indicating where you found them, you have to also indicate how high or how low it reached. So here I'm looking at the local maximum value that we have, right? Comes out being the function value at, so where was that at? Negative 3. So f of negative 3. Right? And this is where, see, you're substituting negative 3 into your original function, which is pretty high power. 7 times the negative 3 cube minus 189 times negative 3. So you guys go ahead and complete your calculation for me.
I got
Okay.
378.
Did you say 378?
Yeah.
378. All right. Thank you. So we found so that here is the local maximum. It hits up as high as 378, but we found it hits to that value at x equals -3. Okay. So now I'm going to make similar conclusion that the function f of x, right, has a local minimum, and that we found that at x equals 3 right from the chart right here. There you go. And so the local minimum in this case right here, the value for that, the actual value, how low it hits down, is found by substituting x equals 3 right, into the function. And then we're going to look at 7 times 3 cubed minus 189 times 3. Okay, so go ahead and run your calculation for me.
-378.
So I hear -378. Okay. All right, thank you. All right, so now that's the end of our problem right there. We found, and so in this way right here, someone in class brought up that question that should we write the answer as -3, 378 right here. I mean, technically it's not wrong, but in my understanding, I don't prefer this way. I prefer, being clear about where you have found the local maximum or the local minimum and how high or how low it hits right here. Simply writing that as a point is to me is too brief right there. Okay, so in my class at least, when you in my class, then let's not write it as a one point like that, but you write it as where you have found it and how low it hits or how high it hits. Okay.